Hello everyone, my name is Charvel, and today we are going to be looking at integrals, specifically how something called a Riemann sum can be used to approximate the value of an integral. There are many definitions of an integral that you're going to come across, but a common one that you might learn early on is that the integral of a function can be thought of as the area under the curve bound by the x-axis. Let's take a look at what that means. Here I have a pretty simple function, f of x equals x, and I've drawn the curve from x equals 0 to x equals 3, so we can see that is simply a straight line. Looking at our definition of an integral as the area underneath this curve, we can say that the integral of this function with respect to x from 0 to 3 is just the area of this shaded region. The graph shows us that we can form a triangle by enclosing the curve with its right bound and the x-axis. Therefore, we can rewrite this integral as the area of this triangle. We know that the area of a triangle is simply 1/2 times its base times its height. So what we can do is simply plug in these values given by the equation. So we know that the base is simply going to be the distance the curve travels on the x-axis, so from 0 to 3, which means our base would be 3. The height is simply the tallest point of this triangle, which would occur at x equals 3, and the value is 3 since y equals x. So the area of this triangle can be written as 1/2 3 times 3, which gives us 4.5. This is a pretty simple way to see that the area under a curve can just be calculated using simple geometric equations if we know how to take the area of the shape. However, sometimes that might not always be the case. Sometimes the curve that you're dealing with isn't going to be a standard geometric shape whose area can be found using a simple equation. Something like this, which I've shown here, the graph of f of x equals 1/2 x squared. This, we can see, is an upward-facing parabolic curve. We don't know how to take the area of this shaded region, since it's not something like a square or a circle whose equation we already know. So, in a situation like this, we can approximate, this is what these squiggly lines mean, we can approximate the integral of this function, just like how we did in the previous problem, the integral from 0 to 3, with something called a Riemann sum. So here, what I'm going to show you is how to do what's called a right Riemann sum, where n equals 3. Now that may sound confusing, but I'll help you break it down and understand what each part of this expression means. What a Riemann sum does is basically split the area under the curve into a bunch of smaller rectangles, like I've shown here for our example. What this means is we can just take the areas of these individual rectangles, whose calculation we know, and add them all up to get the total area under this curve. This symbol over here, called sigma, is what tells us that we need to sum up all the individual areas. So, to break down this somewhat complicated looking expression, let's start with this delta x, which simply tells us the width of each of our rectangles. The way it's calculated is with this expression, b minus a over n, where b is the upper bound, in this case 3. A is going to be our lower bound, which in this case is 0. And b minus a simply represents the total width of this area. We can say that this area goes from 0 to 3, meaning it will have a total width of 3 minus 0, which in this case is just 3. So when we do 3 minus 0, we get 3 in the numerator. Our denominator is going to be the number of rectangles we want to split this area into. In this case, we are given that n is going to equal 3, which is the same as this value for n up here. It's simply saying that we want to split up this area into 3 rectangles. So if the total width is 3, and we want to split up the area into 3 rectangles, each rectangle is going to have a width of 1 unit. Now, the next part of our expression is what we are multiplying delta x by, which is f of x sub I. All this is saying is this is going to be the height of each of our 3 rectangles, as you can see here. The reason you don't see a third rectangle here is what we're doing is we're taking a right Riemann sum. That means each rectangle is going to take the height of the rightmost value. So you can see for this rectangle, which is from x equals 2 to x equals 3, its height is going to be the value of 2 of this function, which in this case is 2, because 1/2 of 2 squared is 2. This is why our first rectangle is not present. The value of 0, the value of this function at 0 is 0. So our first rectangle actually does not contribute to our area calculation. This wouldn't matter with more and more rectangles, because the smaller and smaller this distance between each subdivision is, the more and more rectangles you have underneath a curve, which means the more accurate your area calculation is going to be. Now we can actually perform the calculations for our right Riemann sum. Here you could see we have 3 individual calculations for the 3 rectangles that we have split up this area into. Our first rectangle has a height of 0 and a width of 1. Our second rectangle has a height of 1/2, because the right Riemann sum takes the value of the function at 1 for this rectangle. 1/2 x squared evaluated at 1 is 1/2. Same thing, the width is 1. And finally, our third rectangle, as I said before, will have a height of 2. Adding all these up, because that's what summation tells us to do, gives us a total area of 2.5. Now, if we look at this graphical representation of these individual rectangles, we can clearly see that this method leaves a lot of space underneath the curve that is unaccounted for, especially since one of our rectangles doesn't even exist. Since the rectangles never fully touch the curve, this is why our area of 2.5 is much less than the actual value of this integral, which works out to be 4.5. But if we were to increase our number of rectangles, say to infinity, we would get a much closer representation, to the point where if the limit of n as n goes to infinity is taken, we can equate this value to the integral itself. However, this was simply a much simpler example to show you exactly what a Riemann sum is and how splitting up the area underneath a curve can make it easier to calculate the integral. Thank you for watching.